Hello, my name is Wan Alif Hazik. I am a student from the Energy University. This is a video to demonstrate on my final class project for subject EEEB1034 Digital Logic Design. The task is to design a synchronous counter that counts on the sequence on my student ID, which is 0107806. There are also two bonus tasks. The first bonus task is to upgrade the design of my counter so that it can also count on the reverse of my student ID. And the second bonus task is to design the counter with any other type of flip-flops. So for the first design, I will use T flip-flops to design up and down counter that counts on my student ID. And then for the second design, I will use D flip-flops to count on my number ID. Okay, firstly, let's draw the state diagram. So this up and down counter has two types of sequence. The first sequence is forward sequence, and the second sequence is reverse sequence. So for the forward part, the counter will count on 0107806. And for the reverse part, the counter will count on 608710. Unfortunately, I cannot just use straight away these numbers to build the excitation table, because if I were to derive a Boolean expression based on the excitation table that used this number, it will cause a contradiction condition. For example, if we look on the forward sequence, during the first count, after 0, the number is 1. However, during the third count, after 0, the number is 7. And during the sixth count, after 0, the number should be 6. So these three conditions is contradict to each other. So we cannot use these numbers. This is because they are repeating zeros in the sequence. For the counter, each number should be unique. So what we have to do is we have to differentiate each of the zeros. So first, let's list down the numbers. So there are 3 repeating zeros here. What we have to do to make them unique is we can just add another digits in front of them to indicate that this is the first 0, this is the second 0, and this is the third 0. So let me just put digit 0 in front of the first 0, 1 for the second 0, and 2 for the third 0. So by adding these 2 bits, each zeros is unique because they are not same anymore. And for the other numbers, we can just add 0 in front of them. So if you look here, the numbers are not same anymore. And we can build the counter by using this 6-bit, but for the output, we just display the first 4-bit here. So based on these numbers, the state diagram for the counter should be like this. For the forward sequence, it will be in this direction. And for the reverse sequence, it will be in this direction. So this state diagram has 6-bit number and 7 state. So we should design a 6-bit mod 7 counter. And for this case, up and down counter. So for the early design for the counter should be like this. This is the counter block. So this counter block will have 2 inputs. The first input should be the clock. And the second input should be the input that determine either it will count on forward sequence or reverse sequence. For example, if the input is 0, the block should count on forward sequence, and if the input is 1, the counter will count on reverse sequence. So let's name the input as U. Then the counter will display only the first 4 bits of the number. Let's name the output as W, X, Y, and Z. So the Z here will be the least significant bit, and W is the 4th bit of the number. Okay, next let's construct the state table. So during the forward sequence, the input U should be 0. And then let's just list the sequence on the present state. So for the next state, the number should be a number that will display after the present state. So for example, if the display number is 0, the next state should be 1. And if the display number is 1, the next state should be the second 0. If the present state is 6, so based on the sequence, it will count back to 0. So the next state should be 0. Okay, next let's do for the reverse sequence. So the input U should be 1. So for the reverse sequence, it should start with state 6. And then let's do for the next state. If the present state is 0, it should count back to 6. Okay, so this is the state table. So next, let's do for the excitation table. Before we build the excitation table, let's understand the excitation table for T flip-flop. So this is the T input, this is the input for clock, and this is the output. During a positive edge of the clock, if T is 0, the Q should be QO. QO means that the output Q is as same as the previous state. And if T is equal to 1, the Q should be QO0. It means that the Q is the complement of the previous state. So this means that for T is equal to 0, the operation is hold operation. And for T is equal to 1, it is a toggle operation. So by referring to this excitation table, we can build the excitation table for our counter. So if we look at the input TA, we just focus on the state of bit A. So 0, 0 means it will hold. So TA should be 0. And here 0, 0 hold 0. 0, 0 hold 0. 0, 0 hold. So 0. 0, 1, it will change the complement. So the T should be 1. 1, 0, it is changed to its complement. So toggle 1. 0, 0 hold. 0, 1 toggle. 1, 0 toggle. And 0, 0, 0, 0, 0, 0, 0, 0, and 0, 0 all hold. So this is the input of T for bit A. And then let's do for the other parts here. Okay, if you look at the bit D and E here, they are just the same numbers. So we can conclude that the input for TD and TE should be the same. So we just copy the input of TD into the TE part. Let's do for the TF. Okay. So this is the excitation table for our up and down counter that use T flip-flop. Okay, so based on this truth table, I already did a K-map to derive a Boolean expression for each input TA, TB, TC, TD, TE, and TF. So this is the Boolean expression for input TA. There are so many don't care condition here, so I group them accordingly based on group 2, 4, 8, 16, 32, and 64. So I can get the simplest form of the Boolean expression. This is the Boolean expression for input TB. This is the Boolean expression for input TC. This is the Boolean expression for input TD. And for input TE is just as same as input TD. So the Boolean expression is just same between them. And this is the Boolean expression for input TF. So based on the Boolean expressions that I have derived, so the design of the counter should be like this. Because of the counter has 6 bits, we have to use a total of 6 number of T flip-flop. So for a synchronous counter, the input clock should be all the same, should be uniform. So the input for T will comes from the combination of logic circuit based on the Boolean expression that we derived earlier. The input for each logic blocks here should be input U, and also the output from each flip-flop, which is A, B, C, D, E, and F. And then the output from this circuit will just be the first 4 bit. So the first 4 bit is here. And then for the output, we will just take the first 4 bit from the counter. So this is the general circuit for up and down counter using T flip-flops, which will count on the sequence of my student ID. I have built this circuit by using a simulator called CircuitVerse. So let's take a look on it. So this is the design of up and down counter using T flip-flop that will count on my student ID. This is 6 T flip-flop because we have 6 bit in the counter. This is the logic circuit for input TA. This is the logic circuit for input TB. This is the logic circuit for input TC. This is a logic circuit for input TD and TE. And this is a logic circuit for input TF. All of the circuits have the input from A, B, C, D, E, F, and also input U. And the output from each circuit is connected directly according to the output TF, TD, TE, TC, TB, and TA. And we just take the first 4 bit from the counter to display the ID number. So if I want to make the counter to count for the forward sequence, I just change the input U to 0. So it will start from 0, 1, 0, 7, 8, 0, 6, and comes back to 0. For reverse sequence, we just change the input U to 1. So it will count start from 6, 0, 8, 7, 0, 1, 0, and counts back to 6. So this is the final design for 6-bit mod 7 up and down counter that counts on my ID sequence either in forward flow or reverse flow, just by changing the input U here. Now let's move to design the counter, the same counter, but for this time we will use D flip-flops. So for this counter, we actually just use the same state diagram and state table, because basically it will perform the same operation just like the one that we use with the flip-flops. But because of we used a different flip-flop for this time, the excitation table will be different. So let's construct the excitation table for a counter that use D flip-flop. Okay, before that, let's revise on the excitation table for D flip-flop. So during a positive edge of the clock, if the value of D is 0, the value of Q is 0. And if the value of D is 1, the value of Q is 1. Actually, this flip-flop is just like a register, because if we assign a value 0 for input D, it will register the value 0 for output Q. And if we assign a value 1 for input D, it will register a value 1 for output Q. So to build the excitation table for this counter, it's pretty easy. We just copy the net state into the flip-flop input, because the input for D is just the value of the net state. For example, if you want to assign value A for the net state, so the input for input D here should be 0. And if you want to change the value net state 1, so the input for D here is only 1. So let's just copy this quickly. Okay, this is the excitation table for up and down counter that use D flip-flop. And based on this excitation table, I already derived a Boolean expressions for each input D, DA, DB, DC, DE, and DF. So this is a Boolean expression for input DA. This is a Boolean expression for input DB. This is for input DC. This is for input DD. For input DE, the Boolean expression is just as same as the Boolean expression for input DD. And this is for the input DF. Okay, this is the general circuit diagram for our up and down counter by using D flip-flop. So this is the circuit that use D flip-flop. This is the logic circuit for input DA. This is the logic circuit for input DB. This is the logic circuit for input DC. This is the logic circuit for input DD and DE. And this is the logic circuit for input DF. And the output from each logic circuit will directly connected to their respective D input. If you want to make the counter counts on the forward sequence of the ID number, we just have to change the input U to 0. So the counter should count starts from 0, 1, 0, 7, 8, 0, 6, and then it will repeat the sequence. And if we want to change the counter to count on the reverse sequence, we just have to change the input U to 1, and it will count back, starts from 6, 0, 8, 7, 0, 1, 0, and counts back to 6. So this is the final design for 6-bit mod 7 up and down counter using D flip-flop that counts on my student ID, either in forward sequence or reverse sequence. Okay, we have two circuit which using T flip-flop and D flip-flop. I will include the link for the simulators in the description. And that is all from me. Thank you.